Hi, we are group number 4, and we are pleased to present our project on CFD for simulation of a centrifugal pump. Here you can see a preview of the contents of this presentation. Without further ado, let's dig in. Centrifugal pumps play a crucial role in many industries, such as water treatment, oil and gas, food, and pharmaceuticals, because they efficiently convert the kinetic energy from an impeller into pressure energy. This makes them indispensable for fluid transport in a wide range of applications. Recent advances in computer fluid dynamics, or CFD, have completely transformed pump design. With CFD, we can analyze complex internal flow dynamics, assess hydraulic losses, and even predict cavitation phenomena. These capabilities enable us to accurately forecast performance parameters like head, efficiency, and torque under different operating conditions. Our project's primary goal is to design a centrifugal pump that meets specific geometric and operational criteria. We are using Autodesk Inventor for the CAD modeling and Star CCM Plus for our CFD simulations. The simulation results, covering head, efficiency, and power, will be validated against manufacturer curves. This project builds on previous research that successfully combined experimental data with CFD to enhance pump design. Centrifugal pump design is grounded in classical fluid mechanics and hydraulics theory. Key aspects such as impeller geometry, volute shape, and velocity triangles are essential, as described in foundational text by Golek, Lovanov, and Mateix. In addition, CFD has become vital because it provides detailed insights into internal flow phenomena, a point well emphasized by Anderson and colleagues. Finally, cavitation and hydraulic losses are major challenges in pump design. Studies by Simao et al. And Caridad et al. Illustrate that CFD is essential to predict cavitation onset by capturing local pressure fluctuations and flow separations. Integrating these insights with experimental validation, supported by Pineda et al., helps us make informed design decisions that ensure our pump is both high performing and reliable.
As we can see in Table 1, there's a list of parameters and values used for the specifications CAD. Also in Table 2, we have the centrifugal pump specifications for the CFD used for the star simulation. Herein we used a K epsilon turbulence models, which is a computational approach that uses two transport equations for the turbulent kinetic energy and the dissipation rate to predict internal flow behavior with experimental performance curves. As we can see in Table 2, there are two highlighted Reynolds numbers, which are for water and oil respectively. We can see in water that this extremely high Reynolds number indicates a strongly turbulent flow, making the K epsilon model an excellent choice. While in oil, here's a lower Reynolds number due to its higher viscosity. It's still, this is well within the turbulent regime, which means that the K epsilon model remains appropriate for this lipid too. Also, the properties used for water oil, the geometry restrictions, and the water and oil flow rate used for the simulations are listed in the tables 3 to 5. Now we're going to talk about the results obtained from the simulations mentioned before, and we're going to do a discussion of the results obtained. First of all, in order to determine the most favorable number of cells of the simulation in terms of computational cost, efficiency, error, and accuracy, three different mesh sizes were evaluated, including coarse, normal, and fine, as we can see in table number 6. The results obtained from these simulations provide critical insight into how mesh refinement impacts the reliability of computational fluid dynamic simulations and also the applicability in real life scenarios. In the next slide, we're going to talk about the results and the discussion of these.
The results highlight a trade-off between computational cost and accuracy across different mesh configurations. While the fine mesh with the highest number of cells provides slightly more detailed results, it significantly increases computational time. So conversely, the coarse mesh with the lowest number of cells offers a more balanced approach by maintaining accuracy while optimizing computational efficiency. The comparison with the manufacturer's mesh behavior suggests that excessive refinement does not necessarily improve agreement with the real system. It in some cases it may even introduce artificial effects that degrade prediction accuracy. In conclusion, the coarse mesh emerged as the optimal choice for simulating the pump's performance. It achieves the highest efficiency and total head while minimizing computational errors and reducing processing time. The pump curves were generated for head efficiency and brake power. When comparing the experimental data of a centrifugal pump, it is observed that the behavior of the curves for both fluids is very similar. However, the different operational reports indicate a significant reduction, highlighting the need for a more detailed analysis to improve the considerations in the CFD simulation of a centrifugal pump. When evaluating the results with different fluids, it is crucial to emphasize that fluid properties significantly affect the pump's performance and efficiency. When viscosity is sufficiently high, the flow regime can become laminar, altering the pump's operation. In such cases, friction losses increase, reducing both flow rate and head. Additionally, resistance to flow increases the pump's operational demand, leading to increased energy consumption. Furthermore, the presented figures show a deviation greater than 10% in most data points of the head curve. However, efficiency exhibits a deviation of less than 10%. The lack of accuracy concerning experimental data may be due to the CFD simulation not adequately considering losses caused by roughness or the effects of bolted wall components. An optimal pump design is crucial to minimizing losses due to mixing, friction, and leakage, which would improve the accuracy of the simulation results.
Another important point is cavitation. Cavitation occurs when the local pressure of a liquid drops below its vapor pressure. It's resulting in the formation of vapor bubbles. For example, water usually has a higher vapor pressure than oil, so it is more susceptible to cavitation under similar conditions. This can be seen in the following figures. As we know, water has a lower viscosity and higher vapor pressure compared to oil, making it more susceptible to cavitation. That's why we compare important points of the pump performance curve, such as shutoff, also an intermediate point when the flow rate was 125 cubic meters per hour, and the manufacturer and our BEP, and finally the free delivery. With this in mind, the simulation with water presents greater cavitation than those with oil. These can be seen in the red area that represents the higher pressures. These are most visible for oil. This is due to the fact that water can pass to the vapor state at lower pressure than oil. And in addition, water lower viscosity allows to the flow more easily, and it can experience like a rapid changes, with the result in cavitation. Uh, Instead, the oil, being more viscous, is not affected by these pressure changes and reduce the likelihood to cavitation.
In addition, a worldwide plus comparison was also conducted for water and oil for five different volumetric flow rates, starting from the shutoff until reaching the group's best efficient point. It is important to notice that this parameter is a dimensionless parameter that determines how refined the mesh is near the walls and how accurately the flow is being modeled in these areas of the pump. In CFD simulations, commonly the required values sit between the range of 0 and 5, and for our project, the values between 0 and 1 were preferred. It can be seen that for oil, the profile does not change as the volumetric flow changes, but for water, it's different. It can be seen that as the volumetric flow approaches the best efficient point, the areas colored in yellow or red decrease, meaning that the worldwide plus values are sitting between the accepted range of 0 and 1. The differences between the profiles of water and oil can be explained because this parameter is determined by the Reynolds number of the fluid studied. As the density and viscosity for water and oil are different, it shows that the profiles will also be different.
Here we see velocity profiles for water on the left at a best efficiency point of 290 cubic meters per hour and for oil on the right at 264 cubic meters per hour. Notice that the oil shows a higher velocity around the impeller. This is because the oil's higher viscosity tightly couples the fluid to the impeller blades, reducing slip. By contrast, water's lower viscosity allows the flow to diffuse more widely. These differences highlight how fluid properties affect pump performance and guide design optimizations.
Based on the velocity profiles, a streamline was also created in order to visualize how this parameter changes along the pump. In this part, we show the manufacturer's best efficient point and the group's best efficient point for water. Similarly, in this part, we show these two volumetric flows, but for oil. It can be seen that in the four figures, the highest velocity values are achieved near the impeller, which is explained due to the fact that this is the part where the fluid is given energy by the pump. But as the fluid approaches the outlet of the pump, the velocity decreases.
Finally, due to the results obtained during the simulations, we can conclude that the coarse mesh provided superior results with higher efficiency and total head, while requiring minimal computational time, making it optimal for the pump simulation. Also, the fluid properties significantly influence pump performance, with water showing greater cavitation susceptibility than oil due to its lower viscosity and its higher vapor pressure. In the same way, the wall-way plus profiles indicate simulation accuracy near the walls, remaining constant for the oil but decreasing for the water as the flow approaches the bed, reflecting the different flow regimes for each of the fluids. In the same way, velocity profiles effectively and efficiently visualize the zones where work is exerted on the fluid, identifying areas of maximum parameters values. Finally, an optimized pump design would minimize losses from mixing, friction, and leaking, thereby improving simulation accuracy and real world performance.